Hello friends, welcome to engineering tutorials. Today we are going to discuss about the current flow in PN junction and the voltage and current characteristics of a PN junction. You would recall that in my earlier videos I shared with you all the introductory concepts of PN junction devices, the method of their fabrication and the modes of biasing of a PN junction device, that is forward and reverse biasing, and also the various phenomena associated with each mode of biasing. So today we are going to discuss about the current flow mechanism in a PN junction device, especially in the forward bias mode, and the voltage current characteristics, the relationship between the applied voltage and the current flow under both modes of biasing. So let's get started. So first we are going to discuss about the current flow mechanism. Now let me show you the figure of a forward bias PN junction device from my earlier notes. So here it is, the forward bias mode. So as you see, and I explained to you earlier, that a PN junction is said to be forward biased if the applied voltage tries to cut or reduce the potential barrier voltage, as a result of which the depletion region thickness decreases. So the p-type end is connected to the positive terminal and the n-type end is connected to the negative terminal. So how does the current flow as a result of it? First of all, the negative terminal, it repels or pushes the electrons in the n-type region, which are the majority charge carriers. They push them towards the junction. The electrons thus travel through the n-type region as the majority charge carrier, or free electrons. They flow as free electrons. So the current flow in the n-type region is due to the electrons, or the majority charge carriers. The electrons flow from the negative terminal through the n-type region. The negative terminal repels those electrons towards the junction, and as a result the current flow in the n-type region only is due to the free electrons. Now, as the electrons cross the junction, they meet the holes, and I would like to remind you that holes are vacant spots for electrons, or vacant spot in a covalent bond formed between a trivalent impurity atom and a semiconductor atom. So as the electrons reach the p-type region, the electron hole recombination takes place. So the electrons, these free electrons from the n-type region, they occupy the vacant spot in the covalent bond, or the vacancy for the electron, or they fill the hole. As a result of which, let me again go back to this. So when the electrons reach the junction, they combine with the holes. and they become valence electrons. So these electrons, how will they become valence electrons, or why they become valence electrons, I will just come to it in the next page, the next topic. But let me go to the next part. They become valence electrons. The valence electrons, or the electrons which occupy the hole, they travel through the p region as valence electrons. So the current in the p region is due to the holes or the vacant spot, and I would like to remind you that the holes are powerful attraction, they hold powerful forces of attraction for neighboring electrons, which come to fill that spot, creating another vacancy in their original position. I told you in my earlier or introductory, the starting videos, about the concept of p-type and n-type semiconductors. Then these valence electrons flow to the positive terminal. Those electrons traveling into the p-type region then flow into the positive terminal. As a result, a current flow takes place. Coming to the concept of valence electrons, or how the electrons become valence, we know that in a p region or in a p-type semiconductor, a hole is in covalent bond with an electron. So when an electron goes and occupies a hole, it actually goes to the valence band or the outer band or orbit of the trivalent impurity atom, let's say gallium. So it becomes a valence electron for that trivalent impurity atom. Let me clear your doubt or the questions that are arising in your mind. Here, see a bond formation in a p-type semiconductor. A gallium impurity having 3 valence electrons in its outer band, it forms a bond with a neighboring germanium atom with 1 vacancy for an electron. It's a hole. This spot is filled by the free electrons from the n-type material. So this is the valence band or the valence band electrons of gallium, and this electron which comes from the n-type region and occupies this whole spot, and the electron borrowed from the n-type, it becomes the valence electron. So that is this valence electron thing. This valence electron, or the electrons which keep on filling the spots, the vacant spots, keep on creating vacancies at their original places. So in order to fill the vacancies created by these moving electrons, some other electron comes to fill that spot, creating further vacancies. So the movement of holes, which is generally the term used, is hypothetical. There is no such movement of holes. It is actually the movement of electrons which changes the position of the vacant spot or the hole. That is termed as the movement of holes. The movement of holes is nothing but the change in the position. It's just like this. There is a hole, let's say there is a hole here. One electron comes, fills that spot, creating another hole here. An electron again comes and fill that spot, creating another hole. An electron from here comes to fill this spot, creating another hole. So the electrons move in this direction while the position of the hole moves in this direction. That's why we say the electrons and holes move in opposite direction, and the conventional current is in the direction of the holes and opposite to the direction of flow of electrons. So I have discussed it in detail in my earlier video, so please check into that. So we are clear regarding the current flow mechanism of in the PN junction devices. Now we are going to switch over to the volt-ampere characteristics. So what is the volt-ampere or the voltage current characteristics? It is a plot between the response of a PN junction device in terms of its current flow when an external voltage is applied across a PN junction device. Now this volt-ampere characteristic plot is studied under three categories. Zero external voltage, that is when no voltage is applied to a PN junction. Forward bias region, when a forward bias voltage is applied, and reverse bias, when a reverse voltage is applied to a PN junction. We are going to discuss these three one by one. First is the zero external voltage. Now when zero voltage is applied to a PN junction, the potential barrier or the depletion layer which exists in the middle of the junction just across it, it does not permit any current to flow. So there is zero current flow when the net voltage applied to a PN junction is zero. So when no voltage applied, no current. This spot is denoted by this position. This is the voltage VI characteristics graph of a PN junction device. So this spot is marked by this where the voltage across the PN junction is 0 and current is 0. When a forward voltage is applied across a PN junction, that is the P-type end, as I told you earlier, when the P-type end is connected to the positive terminal of the battery and the N-type end is connected to the negative terminal, it becomes forward biased. So current flows through it. There is no need to again go to the diagram. I've told you many times. So when it is connected in forward bias mode, there is current flow in the PN junction, but this current flow is not very high. Why? See here, the current slowly and steadily it increases, but it's not very high. So why is that? It is because the initial voltage, this much amount of voltage, this region up to this, is consumed in overcoming the potential barrier. So the forward voltage up to this value is used up in overcoming the potential barrier. The voltage at which there is a steep increase, a sharp increase in the current, is called as the knee voltage. At this voltage, the current increase in the semiconductor is very sharp. So this region exhibits non-linear behavior, this region O, A. Beyond A, that is from A to B, it exhibits ohmic characteristics, linear region. Now this value of knee voltage is generally 0.3 volt for germanium and 0.7 volt for silicon. Now coming to the reverse bias part, this part. So what is reverse bias? I told you earlier that when the voltage applied increases or enhances the potential barrier, it is said to be in reverse bias mode. So the p-type end is connected to the negative terminal of the battery and the n-type end is connected to the positive terminal in the reverse bias condition. So as a result of it, the current flow is negligible. No current flow actually in reverse bias condition, but that is the ideal state. But in practical conditions, some amount of current in the order of microamperes flows. It is because of the minority charge carriers. So let me show you. Let's say this is the reverse bias condition, reverse biasing of a PN junction. Here some amount of current flow takes place because of the minority charge carriers, that is electrons in the p-type region and holes in the n-type region. Now, this current is called as leakage current or reverse saturation current, which is very small in the order of microamperes. But if this reverse voltage is kept on increasing, a point comes when the reverse bias voltage increases the kinetic energy or the vibrations of the minority charge carriers, that is the electrons in the p-type region, and they gain sufficient energy or their kinetic energy increases to that level that they are able to knock out electrons from the covalent bond formed between the impurity atom and the semiconductor atom, releasing free electrons. This lets the current to increase sharply. So the reverse voltage at which this phenomena takes place is called as the breakdown voltage. At this voltage, a breakdown of the junction occurs, characterized by a sharp increase in current. It is due to the minority charge carriers, the kinetic energy increase of the minority charge carriers, which enables them to knock out electrons by breaking the covalent bonds of the semiconductor. Let me show you the graph again. Here, in the reverse bias condition, the voltage is kept on increasing in the negative side, but the current increase is less. The point where the breakdown voltage is reached, there is a sharp increase in the current due to the breakdown on the junction and the knocking out of electrons due to the breakage of covalent bonds. So there are a few key terms which are associated with the volt-ampere characteristics of PN junction devices. This is the breakdown voltage, just I told you now. It is the minimum value of the reverse voltage at which the junction breakdown occurs, which is marked by a sharp increase of current due to the breakage of the covalent bonds and the release of electrons from these bonds. Next is knee voltage, or the turn on voltage is also called. It is the maximum forward voltage at which the potential barrier is completely overcome, is completely eliminated, which enables free flow of current in the PN junction device. The forward current is increased. Then is the maximum forward current. Now it is the highest value of current flowing through a PN junction in forward bias condition without causing any damage to the semiconductor device. So the current flow in forward bias condition that does not inflict any damage to the electronic circuit in which the semiconductor device is used is called as the maximum forward current. Then is the peak inverse voltage. Now it is the maximum reverse voltage that can be applied to a PN junction without causing the breakdown of the junction. Now it is related to the breakdown voltage. So then we have is the maximum power rating. Now this is the product of the maximum power, or it is the maximum power that can be dissipated by a PN junction. It is the product of the junction current, or the current flowing through the junction, and the voltage applied across the junction. The product of junction current and junction voltage. So friends, in this video we discussed in detail about the current flow mechanisms of PN junction devices, their voltage and current characteristics, the plot between the voltage and the current in both zero bias, forward bias and reverse bias modes, and we studied the various key terms associated with PN junction devices in reference to the volt-ampere characteristics. So I hope you like this video. Please subscribe my channel Engineering Tutorials for more such videos on electronics, electrical, communication engineering, etc. Thank you very much.